So what you guys basically tell me then, again, what we're looking at right here is called the northern and southern lights.
This star is not here today.
No.
Okay. Thank you.
You're welcome. Now, again, we already call that these things are called the auroras. And then they actually had two very specific names. We had the aurora borealis, and then the aurora australis. So we had the aurora borealis, and then the aurora australis. I'm going to close down here for us. See the aurora borealis, and then we have the aurora australis. Okay, guess which one's in the southern hemisphere?
Australis.
Australis, very good, right? And we know that because Australis is similar to what country, continent? Australia.
Oh,
Okay. So Australia is in the southern hemisphere. Now, when we think about borealis, you go, okay, where did they come up with this term borealis? Right? Well, basically, it comes out of this term called the boreal forest. How many of you guys have heard that term before? Maybe not know what it is, but I've heard of the term boreal. Have you ever heard of that before?
I've heard of burial.
Not burial. All right, boreal. Basically, when we look at the world, we have a lot of different regions. In fact, if we're going to look at this globe, what sits right through here? This whole stretch of South America. Brazil, okay, but what type of forest? Rainforest. In fact, if you follow 23.5 degrees south, 23.5 degrees north, all the way around the entire globe, guess what you have? You have tropical rainforest. And so those are what we call the tropics. That's what we call them, tropical rainforest. What you have in the northern hemisphere, starting a little bit farther north than us, but going all the way up to the 60-degree line, is you have one continuous pine forest belt that goes across the entire globe. So basically takes up the majority of Siberia, all the way through the northern parts of Europe, continues across through Canada and parts of the United States, and goes across the entire thing. We call that the boreal forest. It's basically this large pine forest, conifers. And that takes off, like I said, it's just one belt and goes across the entire globe. So when we talk about boreal, that's the type of forest we're talking about, is pine forest. So when we talk about the aurora borealis, that's because these are typically seen north with these boreal forests. In fact, one of the pictures I have on here, you kind of see pieces. Ooh, that was a bit much. You can see pieces of that boreal forest. I think I have that picture up here. All right, so right here we see the trees. Okay, so that's the boreal forest, parts of the conifers. So that's the auroras. Now, in your research, you want to find out how they work. How are they formed, guys? This is a test question. This is your homework question.
They formed when the sun's protons and electrons travel around the magnetic field.
It's when they travel around the magnetic fields. So remember, we showed you guys the magnet. You had those magnetic fields. So let's kind of come back to this question here. Here's some more pictures. Notice how far above the Earth the auroras really are. So they're not actually part of the atmosphere. They're not part of the sky, so to speak. They're actually kind of above Earth and are on the outermost edge of our atmosphere. So while on the ground, they look like they're in the sky, they're really, really high above Earth. And then this is our magnetosphere. Kind of looks like a giant spider.
20 meters.
So this is kind of what. So this is what Abby was talking about here. Notice we have these fields right here in the front, correct? What's happening to those fields is as the sun's energy is coming in, so in comes the sun's energy. The energy from the sun actually releases protons, which are positively charged. The magnetosphere is negatively charged. So how do those two things interact? The magnetosphere is negatively charged, and the sun's particles are positively charged. They're attracted to one another, right? What happens is the magnetosphere actually gets bent, it gets distorted. And most of the energy, you see this bow out here in the front? Most of that energy is then diverted away from Earth, which is the whole point of the magnetosphere. It actually basically deflects all the sun's really nasty particles. How many of you guys have heard of alpha particles? Have you heard of those before? Gamma rays? What's the problem with gamma rays and alpha particles?
They hurt people.
Why do they hurt people? Yeah, I'll put it to really simple terms here. Gamma rays are very, very small wavelengths. Very small. It's as well as the betas and the alpha particles. They're really small, but they're really massive. But they're really small. Okay? So here's what happens. These rays and particles are small enough that they can go through your skin. Think about X-rays. Okay? So think about what an X-ray does. Now amp that up a little bit, and that's where gamma rays are. Okay? So gamma rays are a lot stronger than X-rays. So gamma rays are able to go through your skin, just like an X-ray is. Well, what's even cooler is they can actually go through your bone. Because they're really small. Really, really, really short wavelengths. Not only that, but they're also small enough wavelengths to go through the cell wall within your cell. And then they're even smaller yet because they can continue into the nucleus of your cell. And then they're even small enough that they start interacting with your DNA. They start kicking out those proteins that make up DNA. And then all of a sudden, you now have a mutated cell. Okay. So gamma rays and alpha particles, beta particles are really nasty. Okay, they start screwing up with your DNA. Lots of bad things happen after that.
3 arms.
So we can make gamma ray filaments and mutate people with them?
Yes. Takes a lot of energy though. Now, I want to come back to this again because this is kind of important. We're going to be, because you're going to hear me talk a lot, but it's really important that you understand the process, not just what this is. You know, I want to make sure you understand the whole process of this. So we come in and we look at this magnetosphere. Most of the sun's charged particles are going to get bounced off and then dragged out. They're going to be kind of deflected away from Earth, protecting our atmosphere. But not all of them get deflected. In fact, where do you think, based on this image, where do you think most of those ions are able to enter our atmosphere? Let's ask that again in a different way. Suppose those were force fields, which they kind of are. And you want to lead an attack on Earth. Are you going to be successful with a head-on attack?
No.
Why not?
That's where front line is.
That's exactly. That's where the front line is. And when that gets pushed back, what happens is it actually gets kind of squished. And so you get this distortion out in the front. So you kind of get this bow look out in the front. But then, so that's definitely not a good idea.
So you go around the flank and
So we go around the flank. Good. The problem with around the flank is we also have more fields around the back. Well, where are these fields the weakest? Look at the image. Where do you see a gap
on the
in
6
the
o'clock.
fields?
On the rear side.
Close. Do you guys see these gaps right here?
2 o'clock.
You guys see those gaps? And come into the middle, where are they at?
At us.
They're at the poles. Where do we see auroras?
At the poles.
At the poles. That's why we see them at the poles. That's because that's where the magnetic fields are the weakest. The reason why they're the weakest is because, remember we saw earlier with the magnet we had up here? Right here we have these magnetic fields that are coming out, they're coming out parallel. So there's a lot of gaps in between the magnetic fields, and that's why the poles are the weakest areas. I know you guys are totally not into this today, but I really need you guys to pay attention. Okay, because this stuff is on the test, which is in 2 days. So again, this is all about process. I will guarantee you that these questions will be on the test. Explain to me how auroras are created, and putting it in one sentence isn't going to fly. Okay, so you need to know the full story here. So we start off with negatively charged magnetosphere. We have ions in our upper atmosphere. The sun's particles come in, just like we're seeing here, and they interact with those particles. And most of the sun's energy is deflected. But we're weakest at the poles, because our magnetic fields are all parallel at the poles, so there's big gaps that the sun's energy can get in. And then what happens is when they actually come in contact, when we just talk about the sun's particles have a lot of energy. Enough energy to mess up your DNA. So then what happens is when those two particles come together, the ions in our upper atmosphere get really excited. And their electrons start flying everywhere. And then they have to release that energy. And they release that energy in the form of light. It's very similar to neon lights. Very similar. Someone explain to me how neon lights work. Doing a lot of explaining. So anybody actually know how they work? I mean, other than you just plug them in and go?
Isn't it something to do with like the oxygen atoms burning and the nitrogen molecules?
Kind of. Basically, neon lights are filled with your noble gases. Neon, argon, xenon, and each one of those has a unique light that's emitted. And what happens is when you pass an electrical current through them, the electrons get really, really, really excited, and all of a sudden you have light. That's exactly what's happening here. We have these charged particles in our upper atmosphere. When the sun particles come in contact with them, they get really excited. The electrons go crazy, and all of a sudden you have light. Yes?
So is the magnetosphere what creates the magnetosphere?
Yes, if it was not for the magnetosphere, we would not have the northern lights. So it's actually the northern lights is an interaction between the solar particles and our magnetosphere, the charged ions in the magnetosphere. It's that full interaction we were just talking about. Kind of some more stuff to talk about with this. What you're really seeing when you look at northern lights is this war between solar particles and then the Earth kind of protecting itself.
So we need to fight that.
Well, there is my map, which is the lights. What happens, unfortunately, is that the northern lights, again, is kind of like the last bit of defense. That's really happening. But there's still some of the particles that are coming through. And every single time that we have a solar storm where our magnetosphere cannot keep up, the sun's particles actually whip away pieces of our atmosphere. A little bit by a little bit, we're actually being stripped of our atmosphere particles.
Oh no.
Okay, so again, we talk about Mars not having water. Well, Mars has a very, very weak magnetosphere. So what happens is when those solar particles are hitting Mars, it's actually taking away pieces of its atmosphere. So Mars has a really thin atmosphere as well. So what that does is then all the water that was on the surface of Mars evaporates, and basically there's no way to control the temperature of the surface. So all that water evaporates into the atmosphere, and then more solar particles are coming in and whipping away those water particles. And over billions of years, all the water on Mars has simply gone away. So that's why Mars doesn't have water. Yes.
Is there only like certain times of the year that the northern lights show?
No, it's not like every single time you go to Alaska you're gonna see northern lights. Nor is it a particular time of year. It'll happen year round. What you'll see though, well, I say that, but you see the tilt of the Earth too kind of makes a big difference, right? Because if you're pointed away, in this case, let's say we're in the middle of winter, as we're getting near there. So here's our sun. As I'm pointing away, so like we are here, this is the sun coming in, we're not really going to get strong auroras. But when you're pointed near during summer, you'll get a stronger connection. Okay? So you'll probably see more during the summer than the winter. But they can happen anytime, they can happen year round. I know I've seen them from Michigan once or twice in my lifetime. I'm not sure if you can see them this far south. That would have to be a heck of a solar storm to see this far south. Yes.
I have two friends from Alaska, and they said that the farther north you go, the more chances that you'll see them, because they're from Fairbanks, Alaska.
Okay.
And they said that it happened like once or twice, every once in a while, and then like the farther, but like if you go up, she said like if you go to like Norway, which is farther north than that, you can see them like probably every night.
Oh, really? So it's almost a constant.
The farther, like she said, like if you stand right up at the pole
Mm.
and stuff like that, she's been in Norway and places like that. If you stand like right up there, you can see them.
No or Norway?
Norway, like where Norwegian people are.
Really?
Yeah.
That's pretty cool to travel to Norway.
Yeah. She said like just the farther north you go, the longer you can see them.
Yeah, that actually, I would love to see the auroras. That's one of my lifetime goals, to get up there and actually see them.
Yeah.
So that's basically the auroras. Now, sometime this year, we had a solar storm and they were telling you guys to be ready to lose your cell phones. Has anybody ever had their computers plugged in and lost them because lightning struck their home? What's the whole point of a surge protector?
So overloaded.
It's to protect against what?
Electrical overload.
It's to protect against a surge of electricity. That surge of electricity basically fries all your electrical components. And so the whole point of that little strip that you guys don't want to look, okay, it's just a power strip, it's actually a surge protector. And what it does is when you have this sudden surge of energy coming through there, it's supposed to basically downgrade that so it doesn't blow up your instruments or your electronics. What happens when we have solar storms, you have this sudden, really large push of electricity of those charged particles flying out through space. We call that solar wind. And it really is this blast of charged particles just flying through space. And even though we have our magnetosphere, what kind of stuff is floating out here around the Earth? Really kind of important stuff that you guys don't think about every single night. But you should. No? They look like stars, but they move.
Space. Satellites.
Satellites! Your cell phones only work because you have satellites picking up signals and reflecting those signals. That's the only why they work. Well, when that solar wind comes in, the magnetosphere can't keep up with it, and it fries the satellites. So guess what you lose?
Everything.
You lose everything. You lose your TV, you're going to lose your TV connection, your cell phone connections, all your wireless connections, all that's gone. So when we think about this, this is kind of a big thing to keep in mind when we talk about it. And then lots of bad things happen. 1989, we had a large one that basically fried the entire northeast of the United States. Was without power for almost a full week. Because the solar winds came in, so solar storm, and basically all that energy fried the electrical stations. So this is actually what's left over after that electrical storm. Literally fried the machine. So solar storms are nothing to laugh at. And they do affect us, although you guys probably for the most part are more interested to see what your friend's doing at home rather than what's going on around you, which I think is amazing. Actually, speaking about cell phones, the commercial, the guy walking around with his little cell phone, and it's like he's like the center of attention, right? I guess in this commercial, the guy's just sitting down looking at his cell phone, doing something on his phone, and he's walking everywhere. Got his little hoodie up, walking everywhere, and then everywhere he goes. But the whole world is going around this guy. He doesn't see a thing. And this is an ad for cell phones. So that kind of bothers me when I watch you guys. You guys do the same thing. Completely oblivious as to what's going on around you. Heads down, hands on the cell phone, and life is happening all the way around you, and you don't even know this. Sad. To me, that's the saddest thing in the world. Which then I think sometimes karma takes over because then people step out in front of the buses while they're texting.
Driving.
One for the universe. Thank you. Those are the ones that deserve to get hit by a bus.
Holy crap, you're so mean.
They do it all the time. Seriously, I guarantee you. If you go to New York City, actually look at their statistics.
So you're saying
The
that
majority of people who are getting hit by these buses don't even notice what's going on in front of them. They have no clue about what's happening, and they're just texting. Pow! Done.
I was about to say it's karma. You can't text and walk in big
Yeah.
cities.
And they're dangerous. I mean, it's almost as dumb as texting while driving. It's nearly about the same level of. Thank you. I want to try to say that. Alright, so guys, that's basically Magnetosphere. Simple as that. Lots of cool pictures to talk about. So right here we kind of see this again where we're coming in. This is what we call the polar cusp. And that's basically the weak spot of our magnetosphere. We can set the poles. And the reason why that is because the magnetic fields are parallel. Okay, so it's really important that you guys know that.
you're saying this would be more
And normally, without the solar interactions, this is what our fields look like. Okay, we're nice and round. But then, okay, this right here is exactly what it says. If you can imagine a big boulder in the middle of a stream, what does the water do in the front of that boulder? Kind of gets pushed off, right? But then what happens behind that boulder? The water goes parallel, way beyond the boulder, and eventually comes back together, right? And you have this calm spot back behind it. And that's basically what we have here. So you can imagine this being the boulder and the stream. You have this buildup of energy in the front, like the water, building up in front of the boulder. And then all that water is being dragged out behind the boulder. And that's basically how our magnetosphere works. You want things like that. You want the big boulder and the boulder of the stream. Alright, so that's pretty much it.